So thanks to Cerner and thanks to Rob and his team for having us here and the opportunity to bring this contents to you folks. Hopefully you're going to find this interesting. By the way of introduction, so my name is Prasad Radhakrishnan. I lead a team that focuses on the intersection between platform and data engineering. Predominantly, we are from a data engineering background, but we focus on the intersection between platform and data, so which brought us closer to Kubernetes, and having had some exposure to Kubernetes over the last year or so, we are also engaged in some of the initiatives to bring stateful data services onto Kubernetes, like Cassandra, Kafka, Spark, and so on. And this is Amey. Amey is from my team, and he is also a data engineer.
Hey, guys.
So before I jump into the contents, a couple of disclaimers. One, so we are going to present to you Kubernetes from the perspective of a practitioner more so. So although it is a generic introduction to different Kubernetes concepts, we are going to approach this from what does it take, or when we are going to use Kubernetes to deploy different kinds of workloads, what are the concepts, all the topics that you would want to know. So we're approaching this from that perspective. So just to get a feel for in this crowd, like trying to get a sense for how many folks are from between application and data background, how many are from app dev or application development background?
Yeah, including UX. Okay.
Cool. So we got quite a bunch. And people from data background, like could be middleware, messaging, or databases, data stores, distributed systems. Cool. That's good. Thanks. Take two. Okay.
Slow.
Okay, so what is Kubernetes? It's an open source system for automating deployment, scaling, and management of containers and containerized applications. Or in simple terms, it's a container orchestration engine. And throughout the presentation, or even when you dive deeper into Kubernetes, there's one thing that will always pop up, which is desired state. So Kubernetes is all about desired state management and how to get there. And you get to define what the desired state is for your applications. So we'll look at the architecture of Kubernetes. It is a classic master worker or master slave kind of topology. So there is a master component. So obviously any master component would require a metadata store to maintain information about the cluster and some state information as well. So for that, Kubernetes uses what is called etcd. Something analogous to etcd would be Zookeeper, right? If you had worked in Kafka or other HDFS-related components, you would have seen that Zookeeper is widely used. In here, etcd sort of takes that place. I thought I had a slide for it, yeah. It's a distributed key value store, and Kubernetes stores all cluster data, including the current state in etcd. Now, the interesting thing here is there is a component called API server, which we'll talk about in a bit. It's only the API server can access or will access etcd. So although all other components want to store data in etcd, it'll be through the API server. Now let's look at the master components. And we're going to highlight some of the critical or the most important components. There's a lot more to it than what we have brought out in this presentation. So in the master, there are three components that you want to know more about. One is the controller manager. The second one is API server, and then scheduler. So what does a controller manager do? It's a control loop. So it is constantly watching or polling etcd through API server to see if there is any job that or anything that it needs to act on. And its job is always to push your workload to the defined desired state. And there are a bunch of such controllers, and we will probably touch on a few of those controllers in the next few slides: replication controller, endpoint controller, namespace controller, and so on. An API server. So the API server is a RESTful interface to access etcd. So pretty much all components will end up storing something in etcd, and it will be through the API server. And it allows you to do standard, HTTP verbs like post, put, delete, get, and so on. Scheduler. So in any distributed system, scheduler is an important component. It knows how to basically go get a workload accomplished. So it's responsible for scheduling your workload. So what does it mean? So it means that it knows how many nodes you have in the cluster and how much resources are available in the cluster, and it knows where to place a certain workload to get that task or get that workload done. And in Kubernetes, there are also some advanced scheduling features. Probably we'll touch on that as well, like node affinity, anti-affinity. Like if a node is bad and you do not want any workloads to land on that node, you could mark that node as tainted node, so nothing goes there. The affinity, anti-affinity as a concept is all about, do you want the workloads to be running on the same underlying machine, or do you want to spread it across the machines? Do you want two pods to be running together or not? So all those things you get to specify using affinity, anti-affinity rules, and the scheduler is sophisticated in a way that it knows what was defined and schedule the workloads accordingly. So let's look at some of the components on the worker side. The workers are also referred to as minions. Now, the 2 or 3 important components in the workers, one is kubelet, the other one is kubeproxy. So kubelet is the agent that tells the master that I'm alive. Like any master-slave architecture, all the worker nodes will have to say that I'm alive, I'm still part of the cluster. So that's going to be kubelet that is heartbeating to the API server so that it can put necessary entries in etcd to say that I'm still alive. And I have a slide for this. So that's what the kubelet does, which is basically heartbeating. And it is also responsible to take the specifications. So we'll look into what a pod is. It is very hard to sort of introduce concepts in Kubernetes in a very sequential way that that we introduce a concept and then use it to explain the next concept, because it's a very vast territory. So what is a pod and what is a workload? We're going to touch on that in a bit. Yep. But basically, when we want to deploy a pod, we will be providing a spec, and kubelet is the one that's responsible to ultimately put that to action. So a scheduler is going to tell, okay, I want this workload to land on node number 22, and in node number 22, as an example, there'll be kubelet that will read the spec and basically get that pod started in that node. Kubeproxy, so every node has this component called kubeproxy. It basically maintains network rules on the nodes, and it also performs connection forwarding. We will dive deeper into the networking aspects of Kubernetes. So container runtime. So when we say container, almost everyone basically assumes it's a Docker container, right? So Docker is one container technology. There are 3 or 4 other technologies that are also used in the industry, like RKT, runC. Now, so Kubernetes is a container orchestration engine, so which means that the container runtime for that container technology will be basically running in the nodes. So it could be Docker, or it could also be RKT, runC, or any of the OCI runtime specific implementation. For more details, you might want to look deeper into what is CRIO or CRIO to understand more about how the container runtime spec works. Now, how does a user or a client connect to Kubernetes? It's using kubectl. And again, kubectl basically establishes connection through the API server. So, just to highlight what I mentioned before, everyone talks to Kubernetes or gets, things done with Kubernetes through API server.
So over the next few slides, we're going to look at some of the basic constructs or concepts about Kubernetes, right? Until this point, we looked at the core architecture, like how the topology is, what is a worker, what is a master. So starting with pod as a concept, pod is like the simplest deployable unit of a compute that you can have on Kubernetes cluster. That is, pod is something that I can take a bunch of containers, and they're always co-located and scheduled together. So that forms a unit of compute inside Kubernetes. And again, workloads on Kubernetes can be set of pods, stateful, stateless, depending on what kind of workloads you want to run on Kubernetes. And Kubernetes itself gives you flexibility to go and deploy a whole bunch of workloads. And we'll go touch upon that later today. We'll actually do a hands-on deployment of one of the stateful as well as stateless workloads as well. So since there are a bunch of containers in this pod, at minimum one, at the max it can go based on what is the capacity of the worker node, all of these containers share a bunch of resources. So inside a pod, they kind of share the network namespace or a storage attached to it, even the loopback and the local IP address for that matter, right? And then if the containers inside a pod have to talk to each other, there's no network call outside of that worker node or outside of that pod. They basically just use 127.0.1 or loopback to talk to each other, thus saving a whole bunch of network bandwidth for you. Now, here's the thing. A pod has an IP address, and that IP address is basically shared across all the containers inside that pod. Now, as and when pod gets rescheduled, or it gets terminated, starts on a new worker node, the pod IP changes. That is the pod ID itself, which is given out to by HCD and master nodes, is assigned a unique IP address and ID to each single pod, and it keeps changing as and when it gets redeployed on the new worker nodes. So let's take a quick look at that. There are a bunch of external applications which want to connect to this pod, and then the pod itself is built with like 3 different containers. There's an Nginx one, there's a Java application, and there's a sidecar logging application, right? This is the simplest classic deployment that you will see to deploy a stateless application in Kubernetes. There's an app server, your business logic in the Java app, as well as logging, or a sidecar application, which will keep taking logs from both of these, streaming to a ELK or some kind of a log aggregator framework for you. Now let's look at how to deploy a container. That's wrong. Let's look at how to deploy a pod. Because in Kubernetes terminologies, you cannot just go and take a Docker container and deploy as a Docker container. You need to go and build it as a pod inside it, right? So if you take a look at the simplest YAML, so everything in Kubernetes is declarative in terms of a YAML file. And the spec itself is exhaustive, but it's easy to get hooked on to write YAMLs. And once you're a Kubernetes practitioner, you just keep writing YAMLs and YAMLs. It's like driving your infrastructure based on the API calls that you write in the YAML spec. So this is the simplest pod deployment YAML that we can have. So if you look at it, there's an API version that you need to stick to. There's a kind or type of a Kubernetes object that is a pod for me, some metadata around it. In the container, there's a name and a name of the container with a version. That refers to the Docker Hub's containers or Nginx container inside Docker Hub and a version spec around it. And I can optionally say, okay, these are the ports that this application is going to be listening to, right? So let's quickly take a look at how we can deploy such a pod itself, right? So we looked at the code. So this is a YAML spec. I'm already connected to my Kubernetes cluster. As you saw before, how do you connect to Kubernetes cluster is by using kubectl or kubectl CLI, which is already, in my case, it's already connected to the API server or the master node itself. So the first thing is kubectl get all. This command gets you a state of your current Kubernetes cluster. That is, sorry, the internet is a little bit slow here, but sometimes it comes back pretty quickly. This kind of gets you the state of the cluster. So right now, there is nothing in the cluster. It's bare bones. There's only one service that has been defined, and we'll get to that later. What does that mean? So I can quickly go and say kubectl create -f. I'm going to take that pod nginx YAML that you see here, just put it up here. As soon as I click enter here, it's going to go and deploy a pod and an Nginx server inside it, and we'll have an application ready for it. So I go click on this, the pod has been created. I can quickly say kubectl get pods -o wide. Okay, so the amount of time it took me to write a command, even before that, the pod went to the running state. So that is actually, it skipped like it went past 4 different stages of pod creation, even before I could type the command and look at it. Now let's look at, on the flip side, what happened behind the scenes, right? When the pod deployment was happening on the Kubernetes cluster itself. Oh, yes, and before that, wanted to quickly touch on a concept of labels, selectors, and annotations. So, sorry, I'll use this. So starting with labels. So in your deployment spec, or any pod spec, you can take the bunch of objects and assign key value pair of a label to it. So this is nothing but a data that has been attached to that deployment spec, which helps you identify later at point during the deployment whether it's based on like an environment, like a dev, QA, test, or whether it belongs to a team or a person. Those are like classic examples where you're going to be using labels. So in our case, we can quickly say, I want to update this pod from a label X to label Y, and the command is as simple as kubectl label pod, and then environment equal to dev. If I want to assign like a label to that pod and say, call it as part of the dev environment. Now selectors, on the flip side, are nothing but a query. That is, I want to go and find all the pods that exist where the label is dev. And based on that condition, I want to do if or else kind of things, or meet certain other conditions. So that's where I'm going to use selectors. And annotations are similar to labels, but you typically would use annotations to have metadata around your objects. So not necessarily related to an environment variable or environment name, but you can have like metadata for a disk, which is fast, slow, medium, or Google, Amazon, VMware kind of thing. Okay, so we deployed a pod. Let's look at what happened behind the scenes, right? From my Mac, I had a kubectl command line installed. It was already connected to an API server. Okay? Now, API server, we first ran a command called kubectl get all, which gave me a quick look at what existed in my Kubernetes cluster, and the answer was nothing other than a simple service that was created there, which is a default one. You cannot delete that, by the way. So once that is done, I went and created a pod. Now, internally, what happened is we took the YAML from it. There was a pod definition inside it. Now, kubectl talks to the API server, and as you remember from the previous slides, API server is the only entry point which writes a state of the Kubernetes system to etcd. So it said, okay, etcd, here's a pod spec, which is going to be Nginx exposed on port 80. That's going to be written here. Now, as soon as etcd gets that information, the scheduler, which is a controller or long-running loop in some sense, quickly detects a change from the API server and says, okay, I see an entry in etcd. I need to go and make sure that this gets deployed as a pod on certain nodes. So my nodes being worker nodes. So that's where it goes and talks to the kubelet on the nodes and figures out, okay, I need to go figure out this node, instantiate a Docker run or rkt run command, instantiate the Docker container itself, that is a container runtime, and give the state back to the API server that I have scheduled this pod on X node and update the state of it. And that's why I got it pod running on X number of nodes inside that. So for brevity, we have skipped some of the other steps. This is a very long process, but it happens in milliseconds or seconds at a time. Now, we looked at single pod deployment, right? And that's not enough. We are developers and distributed systems practitioners. So we want to have a bunch of these pods running. And that's where the fun starts, right? So Kubernetes has a concept called workloads. That means I can take the smallest deployable unit called pod, and I can extend it to have a bunch of these workloads inside it, right? So the simplest one now being a replication controller. That is, I define a similar spec as a pod, but rather than calling it a pod, we're going to be calling it as replication controller, which essentially says that I need to have X number of replicas for a given pod. So assuming I'm going to be deploying a stateless microservice, I can safely assume there are like 6 replicas running, so that connections are coming in, and they round robin, or based on certain weight or certain routing mechanisms, each of the pod gets equal amount of hits from the web service. So the basic rule here being that it needs to be a homogeneous set of pod inside a replication controller. Now, replica set, which was launched about 9 months back, is nothing but an optimization of a replication controller. So you can do a bunch of things inside a replica set, like have a set-based operator or do certain kind of rolling deployments and stuff, right? So as of today, with the latest version of Kubernetes, replication controller is kind of deprecated. We only use replica set wherever required. Now the next deployment or the next workload is called a deployment. That is, it provides a declarative way of defining your workload, whether the workload being pod itself or the workloads being replica sets. So in here, you can do something like blue-green deployments or canary-style updates and deletes of your cluster or rolling upgrades of your version. So let's assume in my Nginx example, I wanted to update it from 1.7 to 1.9, and I had like 6 replicas of Nginx in there. I can choose that any given point in time, I have about 50% of my Nginx service running so that there is no downtime for the end client applications. And this is what deployment allows me to do. So again, deployment and replication controller replica sets are typically used for stateless microservices. Now what about stateful, right? So Kubernetes about, again, 9 months back or so, in version 1.7, they launched a concept of stateful set. That is, it's a controller, which is like a long-running loop, and it's designed to maintain a stateful pod and a life cycle. That is, it provides unique ordering and guaranteeing that pods will come up in order starting from 0 to the number of replicas that you want, and each of these pods have their own simple DNS entry and a persistent volume that can be attached to it, which actually exists beyond the lifetime of the pod or the deployment itself, if you want to. And this is a perfect thing as a building block to go and deploy any of the stateful workloads like Cassandra, MongoDB, ElasticSearch on top of Kubernetes. So later during our talk, we're going to go and deploy Cassandra using the stateful set and a bunch of things that we learned so far in our talk.
Storage? Okay, we'll touch on how storage works in the world of Kubernetes. So there's a concept called volume in Kubernetes. So the basic thing to understand in Kubernetes is that the containers are ephemeral. So if the container wants to store some data, if certain mechanisms are not put in place or followed, one has to assume that the data will be lost, right? Because on-disk files in a container will be lost if in case the container should crash. So Kubernetes solves that problem using the concept called volume, okay? So what is volume? So volume has an explicit lifetime, which is the same as that of the pod, not the container, right? So we need to understand that a pod can have multiple containers. So when we attach a volume to the pod, its lifetime is as that of the pods. So if there's one container in the pod, if it's going to die, you're still okay. The volume will still be there, and kubelet would have just restarted that container, and the volume would be accessible again once the container comes up. But if the pod dies, the volume dies with the pod. So a volume outlives a container, but dies when the pod dies. Now there are a couple of other ways to mitigate even that problem. So assume now you want your volume and data to stay forever or more than the lifetime of the container. There are 2 concepts that's out there in Kubernetes. One is called persistent volume. The other one is persistent volume claim, PVC. And they both are considered resources. So persistent volume is a piece of storage that can be provisioned either dynamic or static, with a lifecycle independent of the pod or Kubernetes itself, because you could pretty much use any of your software-defined storage solutions and keep the volume totally separated from your Kubernetes cluster itself. So if you were to install Kubernetes in, let's say, GCP, you would use Google Persistent Volumes, which has its own lifecycle, and it's not attached to the VM or Kubernetes installation that's going to happen on the other end. And likewise, if you're installing Kubernetes on-premise, probably you want to look at solutions like Scale.io or vSAN, right? So what is PVC? Persistent volume claim is a request for storage by a user. So this could be a little confusing. So basically, PVC is a request, and persistent volume is going to be the actual volume that one could either pre-provision, that's called static PV, and you could also do dynamic provisioning, for which you have a concept called storage class. So we'll touch on that. But PVC is a request for storage by a user, and PVCs in turn consume PV, or the persistent volume, which could have been either static or dynamic. So how does dynamic provisioning work? So there's this whole concept of storage class. So what is storage class? The different storage vendors, it could be even the cloud providers or on-prem storage vendors, they contributed their storage class to Kubernetes so that Kubernetes would know how to instantiate a request with that software-defined storage layer to get a volume provision through code, right? So that is what is called storage class. So it allows on-demand provisioning at the time of request and eliminates the need for pre-provisioning. So storage class defines the profile based on storage specs and policies. And selecting a storage class in PVC triggers dynamic provisioning. So what do we mean by that? So when you are let's say now if you're installing Kubernetes in GCP, you would know what are the storage options available in Google Cloud. If you were to install it in AWS, you would know that EBS is probably your de facto storage option. So for EBS, there is a storage class, and for Google Persistent Volume, there's a different storage class. We'll touch on networking. So we're gonna dump a whole bunch of. So probably networking is the deepest subject in Kubernetes, I want to say, and also there are a lot of new probably concepts that networking is going to bring. So I just tossed a few terms on that slide, so I would encourage you to basically do a deeper dive after the session if that's an area of interest for you on few of these topics. But we will do a high-level touch on networking.
Right. So networking, in general, container networking itself is a vast field, and it has probably taken off in the last 4 or 5 years, right? So it has brought in a whole bunch of new concepts. Some of them you see in terms of headers and here. The good thing is, for a developer, you don't need to really worry about these. It's an ops duty, and the ops team basically goes and sets it up one time based on the workload profiles that you'll be running on your Kubernetes cluster. You're good from there. So as a developer, it's good to understand what it means in terms of how the networking works inside Kubernetes. But in general, the few of the constructs that we're going to be touching upon in the slides later are good enough for you to get started and actually deploy a good amount of workloads on Kubernetes itself. But still, we encourage you to go and look into how it has been done, and it's like a vast field itself. So starting with a fundamental thing that Kubernetes as a concept or a framework came up with, right? That every pod has a routable IP address. Now, how it is assigned from a CIDR range itself is something done by the ops team when they go define a network where these Kubernetes worker nodes and the pods will actually get instantiated. And dynamically, the IP address is assigned to it. Now, the second core requirement is all these IP addresses should be routable inside the network, because Kubernetes cluster is nothing but a bunch of worker nodes and master nodes, and they interact with each other all the time, so it's heavy communication happening. So that's why all these IPs should be routable itself. And again, the pod itself, all the pods on these worker nodes should be able to talk to each other without going through any network address translation. So it should be like a direct route When it comes up, I'm able to ping it, communicate it right from there, right? Now, as we mentioned before, inside a pod, all these containers share a bunch of resources. So from networking perspective, they share the IP address, the local host, the IPC, a bunch of other things itself. And for certain workloads, you can use something called as an overlay network. That can either be a layer 2 or a layer 3 network that can help you alleviate some of the pain from a flat network to go and have this communication done in a more optimal way. So this is where all the networking vendors in the industry jump in and create something called as a CNI plugin. The plugin itself has to be configured by your ops team inside Kubernetes environment on a Kubernetes cluster, which will go and help you optimize your network inside Kubernetes itself. It can be as simple as how quickly you want the traffic to be routed, or as complex as, hey, can I have a publicly routable IP address per pod? And the vast field of options for you in here. And in general, what a CNI plugin does is it just goes and creates a tunnel between all the worker nodes. That is where the compute is happening, right? So it goes and creates a tunnel, either a layer 2 tunnel or a layer 3 tunnel inside this, which helps you optimize the routing and a behavior of how communication is happening inside your clusters.
I think what we want to also highlight here is, so assume you're having a Kubernetes cluster and you're deploying 10,000 applications, may it be microservice, monolith, whatever it is. So which means 10,000 IP addresses need to be provisioned because those pods will have to get its own IP address.
Yep.
So I think that is some of the as a network administrator, one will have to think about how they want to then configure Kubernetes for such a scenario. If they know that there's going to be thousands and thousands of containers landing on that cluster, and probably overlay network is going to be of greater help because it's sort of handled internally.
So at Pivotal, we use something called as NSXT. That's a networking plugin that comes from VMware, which kind of optimizes and allows you to do a lot of layer 3 traffic itself inside of the Kubernetes cluster. So CNI as a concept actually started when the RKT runtime was created by CoreOS itself. And then that's where the plugins started coming in. So right now, the top 3 plugins that we have listed here, Calico, which is from Project Tegera. There's Flannel, which is usually the basic, Flannel, sorry, which is basically a default option for whoever is starting to use Kubernetes. And there is VMware NSXT that we use, which is more heavily optimized for workloads, like stateful workloads in general as well. The next concept we're going to be touching on in the networking is called as a service. So as we looked at pods, the pods have IPs, and these IPs, the pods keep on coming and going, as well as IPs keep on coming and going. So how does an end client application know how should I reach these pods, right? The IP addresses are changing. So services is an abstraction on top of number of these pods. So I can say, for a given set of pods, I define something called as a service, and this service internally has a stable virtual IP address, right? The virtual IP address itself is managed by kubeproxy. So you don't have to really worry about whether this IP address is going to go away. And this is where the service helps you just abstract out these pods, let's say a Cassandra cluster or an ElasticSearch cluster, and the end client applications can just go routed based on a service name or the service IP address or the service's DNS name without worrying about how many pods actually exist. So service kind of helps you even with a lightweight load balancing in some sense. It doesn't really care how many pods exist. It just takes the request, routes it to whatever pod are available. Whether pods keep on coming or going, the kubelet and everything handles updating the service based on that. So virtual IP, as I mentioned, is managed by kubeproxy, which actually watches for all the service instantiations and upgrades. You can always update a service. You can change the name of the service. You can change the backend pod inside it. And as and when these changes are done, kubeproxy goes and updates the IP tables, which are absolutely required. That is where the real record of your services and DNS is kept. in Kubernetes. Now, there are about 4 types of services, right? If I know for sure that the workload that I'm doing is going to have traffic only inside a Kubernetes cluster, I'm going to use a service type called as cluster IP. That is, it will be assigned a virtual IP address, which is routable only inside the Kubernetes cluster, which is also a default service type. That means if I have a Cassandra cluster and if I have a bunch of applications which are going to be connecting Cassandra, cluster IP becomes like the easiest thing for me to do because traffic is going to be limited to my Kubernetes cluster itself. The second type of service is nothing but an optimization or like an option for a cluster IP. That is, I can use this, something called as headless service, which will not have an IP address assigned to it. So all it's going to have is like an internal DNS name and not worry about like having an IP address and a single point of entry to the cluster. This is just being used as a simple discovery mechanism by the pods. And there are a bunch of things that we can do with something like a headless service, and we'll touch upon it later in the demo. Okay, so this is how a simple service spec would look like. The kind of the object is a service. There are a bunch of labels to it. The labels has an app. There's a name for it. The cluster spec is none. That means it's a headless service, as I had mentioned before. And if you see, I'm exposing out a port called 9042, which happens to be like a default port where Cassandra takes the queries for SQL workloads. Now, a couple of other concepts from services itself. At times, you would need to expose your pods to outside services, right? Assuming that the data center has limited connectivity, let's assume for a continuous campus, and 50 miles from here, you need to expose a client application that is going to connect to that service. So a bare minimum option would be to use something called as node port. That is, on every single worker node, it will open up an IP and a port combination, which makes that service accessible to an outside entity directly. Obviously, there are a whole bunch of security concerns here. That's why you need to be careful when you do use node port. You can go and attach certain policies to it. The other type of service is load balancer. That is, you can take the service itself and use IaaS's load balancer, which is something like Elastic Load Balancer from Amazon or load balancer service from GKE, or your internal F5 kind of load balancer if it has an API available to it. And I can take a service and expose it to an outside world with an external DNS name and an IP address just by using the load balancer concept. And this actually takes the traffic as an endpoint and routes it to a whole bunch of other pods that are abstracted by the service itself. And for a load balancer, you obviously need a cluster IP because it can be internal routing as well as a node port on which all these services are running that are automatically created when you create the load balancer type of service. Now, ingress is actually not a service. Ingress is a concept in Kubernetes which allows you to have abstraction on top of a bunch of services itself. So it happens to be a primary way of exposing your services to outside world if you're using HTTP or HTTPS. And ingress internally provides you a bunch of controller options, like HAProxy, Nginx, or any of the cloud providers' ingress mechanisms, like a layer 7 HTTPS load balancer, if a cloud provider has it. And you can, based on the cloud provider, you can assign policies to it, or a weight on how the routes should be displayed, or like how they should be routed inside the cluster. So ingress is one of the more important constructs that you'll be using in your day-to-day life when you start using Kubernetes itself. Okay, now let's take all the concepts that we touched on in today's talk, and we're gonna go deploy a Cassandra cluster, not a single node Cassandra, a Cassandra cluster on top of the Kubernetes environment that we have running. Now, to do that, there are about 4 steps, right? First thing, I need to go and create a service. Now, I want to make sure that Cassandra cluster is reachable. That is from internally inside the cluster as well as externally. So we're going to first go and create something called as a Cassandra service, which is made up of a cluster IP as well as a load balancer service itself. The second thing is, as we had seen before, is a storage class. That is, depending on which IaaS my Kubernetes cluster is running, we're going to go and define a few storage classes, give it some labels and annotations to figure out which storage class a Cassandra should be using so that we are able to deploy the cluster and have a persistent volume where your data will be residing. The third thing is Cassandra is a stateful service. So we're going to create a stateful set after this. And the fourth thing is you can quickly go and check how Cassandra is performing by actually SSHing or running commands through kubectl inside your pod itself. So let's come back here. Let's look at each one of them. So this is a definition for a service. The first one is a headless service because cluster IP is none. The second one is a type load balancer. Cassandra listens to traffic on 9042, which is where it allows you to query using CQL itself. So I'm going to be exposing 9042 as a port in there. The second one is storage classes. So our current Kubernetes cluster is running on GCP. So we're going to be using Google Cloud's persistent volumes. So there are two of them. There is one called persistent disk SSD, and there is persistent disk standard, which is also the HDD option inside Google Cloud. At this point, I'm free to use any of the storage classes, either given to me from the IaaS, or if you're inside data center, as you had seen before, you can have Scale IO, vSAN, cluster, anything that you would want in here. And the last one is a stateful set itself, right? So a stateful set spec happens to be a little bit more complex compared to a pod or a deployment. The reason being that it actually stores state of the cluster, that is your data itself, and you have all the things that you saw today built inside a stateful set. So as you look through, you're going to have what a container I'm using. I'm using the official Cassandra Apache Cassandra container, the ports that we'll be exposing, the environment variables that we'll be setting to make sure that Cassandra is deployed correctly. And at the last, we're going to be defining the volume claims itself. So volume mount is where the persistent volume will be attached to each and every pod. That's going to be at varlib Cassandra data. So if you go and SSH into one of the pods, you're going to be seeing a whole bunch of SS tables when you go to this location. The second thing is I'm going to be having a claim template, and this is where I need to mention what is the type of the storage class I'll be using. So in our case, we chose to use SSDs here. So I'm going to use storage class name as fast, which maps to, in here, fast, which is PDS SSD, right? So let's start deploying Cassandra itself. So kubectl, let's take a look at the cluster again. Let's make sure everything's stable. So we just have one pod running, which is nginx. Now kubectl create -f. So first thing we're going to create is a service, right? So service combined file has both the services, the cluster IP as well as the load balancer. Okay? It quickly goes and creates these services. Now, if you recall from our talk, headless service did not have a cluster IP, while the load balancer actually would go and help me route the traffic from external world. That means it has to get an external IP. Mm-hmm. So after running this command, the service spec would go and request Google Cloud's load balancer that give me an external IP on which 9042 traffic would be routed for those set of pods which are using this type of load balancer service. So this is pending for now because it's an asynchronous call behind the scenes to Google Cloud to go get me an externally routable public IP address for me to go and connect to Cassandra. So until that is happening, we can go and define rest of the stuff. So -f, I'll define the persistent storage classes. It already exists on my cluster, so it's just going to give me an error that it already exists. And then the last step is kubectl create, actually define the stateful set itself. So Cassandra PKS. So I click enter, and if I do kubectl get pods-o, right? You need to be really fast typer if you're using Kubernetes, because by the time you hit enter, the cluster creation is already started. So if you see here, the first pod is coming up, and the status is container creating, which is good. We were faster than Kubernetes itself in here. And since Cassandra being a stateful service, we write a bunch of mechanism to make sure that Cassandra is actually up before telling Kubernetes that the container is up, or a pod is up, right? Now, in our case, the Cassandra cluster had replica of 3. That means it's a 3-node Cassandra cluster that's going to be coming in, right? So right now, the first node is getting up. If I run this command again, so server demo 1, 2, 3. So the cluster is actually up, the Cassandra cluster. And all of them have different age based on when it started. Okay. Now let's look at if our services were actually created with the load balancer IP address, right? So I click on kubectl get service. I see a new external IP has been created, which is routable. So let's see if it's actually routable. So go, ping, I get the ping back from it. It's cool. So I do CQLSH from my laptop, and I'll just try to connect to that. In turn, if you followed our talk very well, it's going to take a request to this IP address and just going to route the request back to all the pods that are being exposed. So from this IP address, I should be able to go and hit all these pods directly, even though the pods are actually running inside the Kubernetes cluster. So I go and do this, pray to the demo gods, and I actually connected. So Cassandra is now connected at that load balancer IP address with the port 9042. From this point onwards, I can go and start using Cassandra. Now, you can be a little bit adventurous and say, OK, this is good for a one-time demo. What if I want to play with Cassandra in managing its life cycle? That is, I want to scale up Cassandra. So it's one command away. All you got to do is kubectl scale replica equal to, I had a 3-node cluster. Let's make it 5. And then, sorry, let me get the name of the stateful set. Give me 1 minute. So, okay, that's it. So I had 3 replicas in Cassandra. After I hit this command, Kubernetes is going to go take the request. I gave it a desired state, which is 5. The actual state is 3. So that means Kubernetes scheduler is now going to go and figure out how do I go and create the desired state, which is 5. So you'll see Cassandra demo 3, which is actually the 4th pod in here, is creating, while the others are like 2 or 3 minutes, or a couple of minutes older, right? I do this again. It's still container creating. This kind of gives you which host node it's on, or which worker node it's on. OK, so the 4th one is created, and the 5th one is pending. So pending state is where scheduler is talking to the kubelet, trying to determine if nodes have enough capacity. Now, in our case, we were like, OK, if there's capacity, go start the cluster. We have no affinity or anti-affinity rules in there. So at this point, the container is creating, container is running. Let's see if I'm able to ping it. Oh, sorry. Connect to it. So connection is fine. Oh, sorry. OK. So at this point, it came back with 3 servers, and then it allowed me to. So it took a little bit of time to go update the service with 5 nodes as IP address in itself. OK. So this ends our Cassandra demo. Now, from this point onwards, it's a simple demo application that we put together, again, using Cassandra on a separate cluster, and deploying an application using Pure Cloud Foundry itself.
Yeah, so even on that note, so what we just demonstrated, Cassandra working on Kubernetes. So I don't think we are touching on CRDs, right?
No, not yet.
So there are other concepts in Kubernetes called Helm charts or operators, that allows you to create sort of a platform managed service, if I have to put it that way. So let's say now you want several Cassandra clusters running on Kubernetes and you want to have a control plane for it, that would know how to specifically do caring and feeding for Cassandra, from a day 2 operations perspective. So all those things can be implemented using what is called operators, which use behind the scenes CRDs, custom resource definitions. So there are a bunch of such projects, that we participate, like bringing a Cassandra operator. We also work closely with Confluent to bring, to get a Kafka operator for, and then Spark and so on. So if there's, interest among the engineers at Cerner to be plugged in to any such open source projects or initiatives, we are happy to, work with you and see how we can, leverage your time, in the betterment of bringing such, community-driven offerings on top of Kubernetes.
Right.
So I think what the next few minutes will take to sort of do a bit more, grand demo than just, installing simple Cassandra. So what we did, we took a lot of, review data from a retail website, and we sort of try to gather some analytics out of, customers posting reviews. So the data set that we have used here, basically behind the scene, it has got 20 million products, 100+ million reviews and ratings from customers. And also, we made an assumption that all those reviews, in a batch mode lands in a blob store. And we just, put together a reference architecture to how do we, take that data, crunch it, and make it available or make some analytics available in a UI. So what would be interesting for a business analyst if you have, such a data set, maybe he would want to look at top ranking products by different categories and know who are your top reviewers and are they having an impact on a product being promoted or demoted among your customers, and then rating histogram and so on. So we, actually they should be able to hit this URL, right?
Correct, so this application is live now, so if you just click on this URL, so it's a bit.ly link. And what we did was, we put our honest effort, we are not UX engineers, so we took all the data and we built something called as a marketplace in here. So this marketplace actually gives you like, what does a single product look like and how are its reviews, how are the ratings being done, the frequently bought together as well as customers who bought this. And then for analytics, or like how a business analyst would look at this data set, you have like top reviewers, you can actually search for products, let's say by beauty or something like that. And at this point,
yeah.
Okay.
So the architecture behind that solution looks like this. So you saw the web app. So web app that you're able to hit from a browser, and the web app is powered by a bunch of microservices that query Cassandra. And how did data get into Cassandra? All the reviews land in the blob store, and we have a data pipeline that basically reads data as and when it lands in the blob store, and it is able to crunch that data or break it down or cleanse it, curate it, and load it into Cassandra. And then we had Spark, which was reading data from Cassandra to derive all those ratings and histogram-related data and write it back to Cassandra. And I think here is the important thing we wanted to highlight as part of this presentation is the abstraction layer, right? If you see, we have Cassandra and Spark running on Kubernetes. So when we say PKS, basically it's Kubernetes. It's just Pivotal's flavor of Kubernetes or distribution of Kubernetes. And you can see that we had the web app and microservices running on PAS or Cloud Foundry, traditionally how it was called, Elastic Runtime. So the key difference here is that the amount of time it would take to deploy a microservice onto a PAS or Cloud Foundry layer is really, really short for us, because that is truly a platform as a service offering. So which means that you are doing a CF push, and very next second, your code gets behind the scene. Actually, it gets containerized, it gets deployed, scheduled, deployed, getting an IP address allocated, and all that is handled by the platform. Whereas, when we deployed Cassandra, we took care of, I may just, explain how all the way from creating a service and how you are going to expose it to the external traffic to the installation, everything is explicitly handled, by the engineer.
Yep.
So for that reason, we have microservices deployed onto PAS, and on PKS, we have stateful workloads running. Cassandra, I think we touched on that. Spark, so Spark from Spark 2.3 officially supports Kubernetes as a scheduler. So we have Spark running there, which means that the Spark executor jobs are the pods that come and go as and when you submit jobs, and we use PySpark and Spark Cassandra connector modules, so we are able to read data from Cassandra. We use Spring Cloud Data Flow as the data microservices that are chained together to basically read data from Blob Store, and then incrementally process the data, enrich it, and put it onto put it on Cassandra.
Yeah. Right.
Is this the last slide?
This is the last
Yeah.
slide.
So
the app is live. You guys are welcome to go look at it. We will also make the source code available so you can actually replicate the entire thing on your clusters. If you don't have clusters, just use your Amazon account or Google account and a credit card that's been given by Cerner or something.
all right, we'll take if any questions. I think we're just on time. We had to
Just on time.
rush a little, but happy to answer any questions.
You can reach out to us at any time. We will keep our contact IDs here. Also, thanks to Rob, Brian, and Brittany for helping us set up this and actually giving an opportunity to talk here. Hopefully you all got good amount of insights from what Kubernetes is and how would actually a developer or an operator would go and use it and get value out of the framework.
Thank you all.
Thanks.